All right, we're back on. So here's what it actually looks like, and I promise I'll work through a example here in a minute. Oh yeah, we were stopped right here. That's right. Let's look at this. Play from current slide. Whoops. All right, and then I want to show you physically why this works, because that's the real cool part. All right, we can sit there and look at. Oh my gosh. Oh my gosh. All right, so here we go. Sorry, I get clicking around on my stuff. What value should theta be so the average intensity of the polarized light reaching the photocell is 1/10 the average intensity of the unpolarized light? Okay, so the average intensity of the unpolarized light is I naught. We want to get something that's 1/10 I naught coming in. All right, so here's what this would look like. All right, that's why I clicked over here on my ladybug. There she is. All right, so here's Malou's law, which says the intensity after leaving the analyzer, okay, is equal to I naught prime, which is the intensity after leaving the polarizer, times the cosine squared of the angle. All right, so we're after the angle. All right, so first of all, here we go. We've got a polarizer right here. Let's draw our polarizer, and we've got our light coming in here. Okay, and this is our polarizer, and then attached to the polarizer is the analyzer, and it is going to be at an angle theta. All right, by the picture, and we want to get the intensity of the light. This is I naught. We want this to be 1/10 I naught when it comes cracking through. All right, so what angle do I need to set the analyzer? Well, first of all, when it goes through a polarizer, it loses half its intensity. Polarizer loses half. All right, so the polarizer, it loses half its intensity. So right now it's at 1/2 I naught when it's traveling through here. And then when it pops out here, we use this equation. So we want, and here's what we want it to be. We want it to equal 1/10 I naught, following Malou's law, is equal to this guy coming out of the right here. So you go to 1/2 I naught times the cosine squared of theta. All right. Oh, well, it looks like my I naughts cancel, but let's multiply both sides by 2, and we'll get 1/5 I naught is equal to I naught times the cosine squared of theta. All right, and so divide I naught out of both sides. Divide that out, and we get 1/5 is equal to cosine squared theta. Take square root of, which is the same thing as the cosine of theta squared, like this. All right, that's just the way we write it. So take square root of both sides. So theta is equal to the inverse cosine of 1/5, the square root of 1/5. If you don't believe me, watch this. And we've got this. We've got inverse cosine of square root of 0.2, which is 1/5, right? Close, close. I got 1.1 degrees. I hope that's right. I'm gonna be really embarrassed, but I don't think that's the right answer. I did it right. What did they get? Oh. Yeah, it's the cosine. Oh, my calculator was in radians. Duh. Ah, that's my problem. My calculator's in radians. Boom. So let's do second entry one more time. There we go. Oh, you didn't get to see it. There it is, 63.4%, or 63.4 degrees. All right, well, let's take a look at one of our homework problems. Real quick, let's take a look at one of our homework problems. All right, on this stuff. Let's look at this guy. So let's do so let's look at problem 7. All right, so here it says, unpolarized light of intensity of 550 watts per meter squared is incident upon 2 polarizers. Okay, the first is polarizing, and then the second, and the axis of the second is rotated to 15 degrees off the vertical. Okay, what is the intensity of the light after it passes through the first polarizer? I'm going to say 225 or 275, right? Because it's 1/2 I naught. What's the intensity of the light when it passes through the last one? All right, so that's pretty straightforward. Let's just set it up, and then we'll take it from there. So for problem 7, let me get the data down, and then we'll talk about it. And I naught is equal to 550 watts per meter squared. All right, so let's go to the good old ladybug here. Got a polarizer here, got an analyzer here. That's off the normal like this, 15 degrees. All right, so you've got 550 here. This would be 275 because that one's equal 1/2 I naught. Now and then what happens is 1/2 I naught, then this guy, I final, let's just call it I final just for giggles. I final is equal to 1/2 I naught times the cosine squared of 15. That's all there is to that, which remember is equal to the cosine of 15 squared. So that's just a straightforward calculation. Not much to that. All right, cool. But now listen, but before we leave this chapter and go on to the next one, which we're going to still do on this same lecture day, because this hasn't been very long, and we can get into plane mirrors and things like that. Let's go back to this polarizer thing. Let's see how it works. Used to show River the effect of polarizing and reducing the glare of light from the surface of the water. If you're at a certain angle, if you're at the right angle, the polarizing takes away the glare. I just saw a thing for like this visor thing. Instead of wearing sunglasses, you pull this visor thing down, and it polarizes the light for you. Basically, is what it's doing. But how do they work? How do they work? All right. So here's off the water, or here's an air glass thing. Partially polarized light, and this gets into Brewster's law is what it's called. Okay, any reflection is going to be partially polarized, and that's why sometimes you'll kind of see, if you look just right, you'll see a black like little circle out here, and you think, oh my gosh, is there a shark in the water? No, it's just the polarization. It's just the shadow. All right, but here's what happens. You got these long molecules in a polarizer thing. Here's its axis. Okay, and then notice, only half, as the electromagnetic wave passes through this, all of these are going to absorb the rest of the wave and cut it in half. Cut the intensity in half is what happens. Okay. And so here they come. Here comes the ones along with it, and then here comes the ones that are opposed to it as the E field goes like this, and they all get cut off. Half of them get cut off and get left behind. So that's what happens. All right. And scattering, polarization by scattering, unpolarized light scattering from air molecules shakes their electrons scattering. So that's, red sky at morning, sailor take warning, red sky at night, sailor's delight. Red light waves are big, goopy things. And so they get smacked back into the atmosphere pretty easy, unless it's a nice, clear, sunny day. So when it's a red sky at morning, we know that things are coming to us from the west. And so when we look at the red sky in the morning, we go, oh, the fair skies are gone. Red sky at night is the sailor's delight. When we're looking to the west, we go, oh, there's not a lot of particles and dust being kicked up, kicking those red ones back, red particles back into the atmosphere. Because the red waves are a lot thicker than the blue ones. So the blue ones are the ones that usually come through, but sometimes we get the red ones on the scattering when they're able to get through and they're not getting pushed around by a bunch of dust that's being kicked up. Anyway, all right, enough on that. Just wanted to, so that finishes up that first little section, but we're going to go on with this lecture as if this was still the same day, all right?